Hi everybody. We're now going to review inverse trigonometric functions. Now the reason we want to review inverse trigonometric functions in the middle of a calculus course is because, as we'll soon see, there are a lot of common functions like 1 over 1 plus x squared, or the square root of 1 minus x squared. There are a lot of common functions like these whose antiderivatives involve inverse trigonometric functions. And so it seems reasonable that we would like to know what the antiderivatives of these common functions are, and they do have a lot of applications in science courses like physics and chemistry. So in order to understand what the antiderivatives of functions like these are, we need to thoroughly understand inverse trig functions. So we're going to do a review of them here in this video. Now, to define the inverse trig functions, we first introduce the arc notation to denote the inverse of a trigonometric function. So for example, the inverse sine function we can denote as this arc sine of x. So that's going to denote the inverse sine function. Now there is some other common notation that you'll see, and we'll talk about that in a second. Now recall that if you're given a function f of x and we let y equal f of x, then that's equivalent to saying that f inverse of y equals x, where this denotes your inverse function for f. Remember, this does not mean 1 over f. It doesn't mean that. It means the inverse function. Now, this is the same as saying that if x goes to y under f, then the inverse function goes backwards. So this means f of x equals y, and so f inverse of y will give you back x. Now this is saying the same thing down here, but we just replace the x with the y and the y with an x. So if y equals f inverse of x, so if this is f inverse of x equals y, then the original function f would go back in this direction. So this is saying the same as this, just with the x's and y's flipped. Now let's use this to develop the definition for our inverse trig functions. Now here we have the definitions for our inverse trigonometric functions. And when you're using these definitions, you should think of the value y as being an angle and x as being a real number. So let's take a look at the inverse sine or arc sine first. That's number 1 right here. So we define y to equal the arc sine of x if and only if the sine of y is equal to x. So for example, we know that the sine of pi over 4, that's equal to root 2 over 2. You can use a standard unit circle diagram to find that, or just use a calculator. So the pi over 4 is playing the role of the y, and the root 2 over 2 is the x. So notice that the y is an angle, and the x is a real number. So then because of this, the arc sine or inverse sine function of root 2 over 2 is defined to be pi over 4. So notice how we're basically using this definition right here, which relates a function and its inverse function. You'll also notice that we always use radian measure for the angle y. Now also take a look down here. The domain of the arc sine function is from -1 to 1 inclusive, and the range is from negative pi over 2 to positive pi over 2 inclusive. So this is the domain of the arc sine, and this is your range of the arc sine. Now let's take a look at this graphic, and this will help us to understand the arc sine a little bit better and we'll also see what its graph looks like. Now, to better understand how the arc sine is developed, let's take a look at what the graph of it looks like. So here we have the graph of the sine function to start out with, and we want to define the inverse of this function. Now you see one problem right away. This function is not one-to-one. So it's not going to have an inverse function. So what we need to do is we need to restrict our view on this function, or restrict the domain, so that it becomes one-to-one. So we're only going to define the inverse sine function for a small piece of this function as follows. So we're going to restrict the domain here to be between negative pi over 2 and positive pi over 2. So this is what our restricted sine function looks like then. So right here we have our restricted sine function, and notice its domain is negative pi over 2 to pi over 2, and the range is from negative 1 to 1. So by looking at this piece of the sine function, we've basically captured all of the sine function. Everything else is just a repeat of this portion of the graph of the sine function. So now we're only going to use this piece right here to define the inverse sine function. And so if we take this graph and flip it about the main diagonal, we get the graph of our inverse sine function. So there's the main diagonal, and let's get rid of the rest of the sine function. So this is the portion that we're going to define the inverse sine function for. So if we flip that about that black dotted line, there's the graph of your arc sine function. And let's take away the sine and the black line, and there we go. So you see this here is the graph of your inverse sine function, or your arc sine. Now you notice one thing about this. The range of this function goes from negative pi over 2 to positive pi over 2, so the y is supposed to be between, so that's the range as we saw in the definition, and the x, the domain of this function, it only goes from negative 1 to 1. We can see that if I change the tick marks on the x-axis there. So there you can see clearly now the domain goes from negative 1 to positive 1. And so we see that the x is going to be between 1 and negative 1. And so there we go. That's how the arc sine is defined. And we see now why the domain is from negative 1 to 1, and the range is from negative pi over 2 to positive pi over 2. Now all of the other trig functions are defined similarly, and we'll take a look at two of them. We'll look at the arc tangent and the arc secant in detail, and then the other ones are defined similarly. And continuing down our list here, we have the definition for the arc cosine. So we say y equals the arc cosine of x, if and only if the cosine of y is equal to x. And you'll notice that the domain for the arc cosine function is the same as the domain for the arc sine, negative 1 to 1. And the range, but the range of the arc cosine function is a little different. The range is from 0 to pi instead of negative pi over 2 to positive pi over 2. And the reason that the range changes here is because when you define the arc cosine function, you start out with the graph of your cosine function. But in order to make this 1 to 1, you have to restrict the x to be between 0 and pi. And then when you define the inverse of this, the domain becomes your range, and this is why the range of the arc cosine is from 0 to pi. Very similar to the way we got the range for the arc sine function. Now here's the definition for the arctangent. Same thing, y equals arctan of x if and only if tangent of y is equal to x. But you notice now that the domain for the arctangent is negative infinity to infinity, and the range is from negative pi over 2 to positive pi over 2, but it does not include the two endpoints. Now let's take a look at the graph of the arctangent function, and that'll give us a little better understanding of why the domain and range are as we have stated here. Now here's the graph of the tangent function. So all of these are the graph of the tangent. So once again you see we have a problem. The graph doesn't pass the horizontal line test, so it's not one-to-one, so we're not going to be able to define an inverse function for the tangent. So what we do is this, just like for the sine, we restrict the domain for the tangent function, and then we'll define the inverse for that restricted domain tangent. So we're going to restrict our domain to be between negative pi over 2 and positive pi over 2. Now you notice that the tangent function has vertical asymptotes at those locations. So let me put them in here. So there's our vertical asymptotes. And we're only going to consider that portion of the tangent function, and we're going to throw the rest away. So there. So now we're only going to define the arctangent for this function right here. Now we have to flip that about the main diagonal. So when we flip the green curve about this main diagonal, the dotted black line, here's what we get. That's the graph of our arctangent function. Now notice something else very important here. If I were to flip these vertical asymptotes around the line y equals x as well, this is what we would get. So you see how those vertical asymptotes became horizontal asymptotes. And notice that the arctangent function, as x goes to infinity, the arctangent gets infinitely close to the value pi over 2. So that's a very important result. So we'll use this result later on. And also you see as x goes to negative infinity, how the graph of the arctangent gets infinitely close to negative pi over 2. That point right there is negative pi over 2 on the y-axis, and this one was positive pi over 2 up here. And also notice that the domain of the arctangent is from negative infinity to positive infinity. Oops, I shouldn't put equal there. Like that. That's our domain for the arctangent. Notice how it's defined from negative to positive infinity. And that's because the range of the original tangent function was from negative infinity to positive infinity. And then our range for the arctangent is from negative pi over 2 to positive pi over 2. Notice how the arctangent, the y values go from negative pi over 2 to positive pi over 2, but they never actually touch, they never actually get to pi over 2, for example, because this curve never actually crosses that dotted line. It doesn't cross the dotted line, the horizontal dotted line anywhere. And so that's how we get the graph of our arctangent. And just keep in mind down here, this is the domain for the arctangent, and this is the range for your arctangent. And just cleaning this graph up a little bit to get a clear picture of everything. So once again, this is the graph of our arctangent, and these are the two horizontal asymptotes for the arctangent function. And so that graphic that we just looked over clears up our understanding of what the arctangent is. And you notice down here we have our definition for the arc cotangent that is defined similarly, except that you notice that the range for the arc cotangent is from 0 to pi instead of negative pi over 2 to pi over 2. And that's because when you define the arc cotangent, you start with, in order to make this function one-to-one, you restrict its domain to x being between 0 and pi. And then this domain becomes the range for your arc cotangent function. Now here we have the definition for our arc secant function. So y equals arc secant of x if and only if secant of y equals x. Now you notice that x is supposed to be between negative infinity and negative 1, or from 1 to infinity. That union symbol right there, that means you just put both of these sets together. So the domain is both this set and this set together. And also notice that the range of the arc secant is from 0 to pi over 2, together with the set from pi over 2 to pi. But notice that you're excluding pi over 2. Notice this is less than here, so the y never actually equals pi over 2, and over here the y is never pi over 2 as well. So your range is from 0 to pi, but you exclude pi over 2. Now let's take a look at a graphic illustrating how we obtain the arc secant function and what its graph looks like. Now here we have the graph of the secant function, and we want to find its inverse. Now the way you get this graph, just briefly here, is remember secant is 1 over the cosine. And so if I superimpose the graph of the cosine on here, you'll see how we get the graph of the secant function. So right there's graph of the cosine function, this black curve here. And you notice that when cosine of x is 1, the secant of x will be 1 also, and that's at these points right here. And then as cosine goes from 1 down to 0, the secant will go from 1 up towards positive infinity. And so you see, wherever the cosine is equal to 0, the secant will have a vertical asymptote because 1 over 0 is an undefined quantity. So the secant will have vertical asymptotes here at pi over 2, 3/2 pi, 5/2 pi, and so on. So that's how we get the graph of the secant function from the graph of the cosine function. Now we want to find the inverse of the secant function. Well, once again, you notice we have a problem. It doesn't pass the horizontal line test, so it's not 1-to-1. So what we have to do is restrict the domain of the secant function. And so we're going to restrict the domain to be between 0 and pi. So we're only going to look at this piece of the secant function. So we're only going to look at this part that's in dark blue now, the solid dark blue curve right here and here. And everything else we're just going to throw away. And let me get rid of the graph of the cosine. There you go. So this is what we have to find the inverse for. So once again, let's take our main diagonal and flip the graph about the main diagonal. Now, notice one other thing here I want to put in this graph. Right there is our vertical asymptote for that portion of the secant function. So now we're going to flip everything about that line, and when we flip it about that line, the secant function will become this. So notice how this piece here became this part, and this piece here became this piece right up here when we flipped about the main diagonal. And also notice that this vertical asymptote right here at pi over 2, that will become a horizontal asymptote like this. So it becomes that line right there. And so taking everything away that we don't need, here we have the graph of our arcsecant function. Now you'll notice that the domain of the arcsecant function goes from negative infinity to -1. That is -1 on the x-axis there. Let me make that a little clearer. So you see this is -1 right here on the x-axis, so our domain goes from negative infinity up to and including -1. And also from 1 to positive infinity. And I just use the union symbol there. That means this interval or that interval. And also notice the range of the arcsecant. Well, the range goes from 0 up to, but it does not include pi over 2. That point is pi over 2 on the y-axis, but you notice the graph never actually crosses that dotted line anywhere. So that is not, pi over 2 is not part of the range. So the range goes from 0 to pi over 2, but we put an open bracket there to indicate that pi over 2 is not included. And then it also goes from pi over 2 up to and including pi. That point is on the graph of the arcsecant. And there you go. We've fully defined what the arcsecant is. Now if you look in most textbooks, you'll see a graphic like this. Here's a summary of the graphs of all of the inverse trig functions along with their domains and range. And you can see, for example, we went over this one, the arc sine, and we looked at the arc tangent in detail and the arc secant function down here. And you see how the arc cosine, arc cotangent, and arc cosecant are defined similarly. Now let's take a look at a few examples. So here we have a unit circle diagram that'll help us with these two examples. So let's evaluate the arc sine of 1/2. Well, the unit circle diagram up here lists the sine and cosine function values for common angles like pi over 6, pi over 4, pi over 3, and so on. So if we look, you see you've got the coordinates on the unit circles labeled here. For example, this point right here is √3 over 2 and comma 1/2. And notice that the √3 over 2 corresponds to the cosine and the 1/2 corresponds to the sine of this particular angle theta right here. And you get those basically from the right triangle definition for the trigonometric functions. Remember, sine is opposite over hypotenuse, so in this picture here your hypotenuse is 1, your opposite side would be 1/2 right here, so that's why the sine of pi over 6 would be 1/2. And in fact, that's going to tell us what the answer to this problem is right down here. So we want to define the arc sine of 1/2. Well, let's notice from this diagram up here, the sine of pi over 6 is 1/2. And so therefore, the arc sine of 1/2 is going to be pi over 6. And there you go. So this quantity right here is pi over 6. Now most calculators have an inverse sine, inverse cosine, and inverse tangent button built into them. You could evaluate this on your calculator and you'll get back pi over 6. Now it may not look like pi over 6, it might be in decimal form, but it will be equal to pi over 6. Let's take a look at this one. What's the arctangent of the square root of 3? Well, looking back here at our unit circle diagram, recall that the tangent is sine over cosine. So let's try to pick out a common angle here where the sine over the cosine will give us the square root of 3 back. So looking through here, it looks like this angle right here, pi over 3 or 60 degrees, will do that for us. You notice the sine is root 3 over 2 and cosine is 1/2. So root 3 over 2 divided by 1/2, that's going to give us root 3. So let's notice then that the tangent of pi over 3, so that's going to be sine over cosine, root 3 over 2 divided by 1/2. Of course, the 2's here cancel, and we get root 3. And so therefore the arctangent of root 3 will be pi over 3. And there we go. So this quantity here is pi over 3. Looking at this example right here, what's the limit as x goes to infinity of the arctangent of x? Well, if you recall from our graphic that we looked at when we went over the graph of the arctangent, that value is pi over 2. And the limit as x goes to negative infinity is negative pi over 2. And so it always comes in handy, as we'll see later on, to keep in mind the graphic for the arctangent function, which looks like this. And recall this is the graph of our arctangent function, and you see as x goes to positive infinity how the graph of the arctangent, the values of the arctangent are approaching pi over 2. That's right there on the y-axis. And as x goes to negative infinity, the values of the arctangent are approaching negative pi over 2. Those are two horizontal asymptotes for the graph of the arctangent function. Now here's some notation that you'll see used a lot of times for the inverse trig functions. We've been using the ARC notation for inverse trig functions, but a lot of times you'll see this written. So in place of arc sine, for example, you'll see this written like that. Now that's reminiscent of the notation if we have a function f, we denote its inverse by f inverse, like that. But once again, keep in mind that this notation does not mean, when we're considering inverse functions, this does not mean 1 over f, right? 1 over f is not the inverse for the function f. So a lot of times you'll see this notation used for your inverse trig functions. Now it gets a little confusing because keep in mind once again that when you're dealing with inverse functions, when you're thinking of this as the inverse sine, it's not equal to, this does not mean 1 over the sine, like that, okay? Although in some context, you know, when we talk about the sine squared x, that does mean sine x times sine x. That really does mean you take sine and raise it to the second power. So it gets a little confusing because this could mean 1 over sine in certain situations, but when you're dealing with when you're thinking of this as an inverse sine function, you're thinking of it like this, not like this. So that's why a lot of people prefer the arc sine notation, but you will still see this used quite often in many textbooks. Now let's take a look at a few examples down here. So here I use the sine to the -1 notation to indicate the arc sine, just so that you're used to it. So we want to evaluate the cosine of the arc sine of √3/2. Alright, so what we want to do here is we want to think of this quantity as being an angle, say theta, in which the sine of theta should be √3/2. And then we want to evaluate the cosine of this, the cosine of theta. Alright, so what we'll do here is, easiest way to do this is with a little picture. So let's label this quantity right here as theta. Now the sine of theta is supposed to be √3/2. So sine, remember, is opposite over hypotenuse. You have to remember your right triangle definitions for your trig functions. So sine of theta, this is supposed to be √3/2. So we'll think of this as being the entire numerator right here. The opposite side, we'll just divide this by 1. So the hypotenuse will be like 1. The opposite side will be √3/2. And then we have to solve for this side right here because we want to take the cosine of theta. Remember, cosine is going to be adjacent over hypotenuse. So we have to solve for this adjacent side right here. Okay, let's just call that distance, that length right there, A, and that's what we need to solve for. Well, A squared plus √3/2 squared, right there is √3/2 squared, equals 1 squared. And so then we can use this to solve for A. So A squared, of course, is going to be 1/4, 1 minus 3/4, and so A is going to be 1/2 right there. So that quantity right there is 1/2. And so therefore the cosine of theta equals 1/2. And that's what this quantity right here is equal to. So this entire quantity right here then we've found is equal to 1/2. And so once again, the way we thought of doing that is by thinking of the inside here, the arc sine part, as being an angle theta in which the sine of theta has to give us back √3/2. And then we formed a right triangle picture like this, used our right triangle definitions to find the cosine of theta. Let's take a look at these. So for this next example, we want to rewrite the cosine of the arc cotangent of 2x as an algebraic function of x, meaning we want to rewrite it so it doesn't involve any trigonometric or inverse trigonometric functions. So once again, we're going to think of the inside here, that piece, as being an angle theta in which the cotangent of theta gives us back 2x. And so let's form a right triangle picture over here then. So if I label this angle as theta right there, remember that the cotangent of theta, cotangent is adjacent over opposite. That's something that you need to remember. Remember, tangent is opposite over adjacent, and so cotangent is going to be adjacent over opposite. Now that's supposed to equal 2x. So let's write this 2x as 2x over 1. And then we'll label the adjacent side as being 2x and the opposite side as being 1. Now we have to solve for the length of this side, c. Well, remember, c squared equals 1 squared plus 2x squared. And so c is going to be like that. So let's just label that right here. There you go. So that's the length of side C. And so now we can just read off our answer. You see, now we want to evaluate the cosine of theta. Well, cosine of theta that is adjacent over hypotenuse. And so just reading off this, here's our adjacent side, here's our hypotenuse, and so we get, and there we go, that's our answer. That's what this quantity is equal to right here. That's what we were trying to find. Let's try one more like this just to make sure you have the hang of it. Let's rewrite the sine of the arctangent of x as an algebraic function of x. So once again, you can pause the video and try this on your own if you like. Let's label the arctangent of x as an angle theta in which the tangent of theta should equal x. And so we'll form a right triangle picture up here. So if we label this as theta, and recall that the tangent is opposite over adjacent, and then that's going to equal, now if we think of this x as being x over 1, we can label the opposite side as having length x and the adjacent side as having length 1, in which case our hypotenuse is then going to have length the square root of 1 plus x squared, right? Using our Pythagorean identity, a squared plus b squared equals c squared, of course. And so then we get that the sine of theta is then opposite over hypotenuse. And so that's going to be x over the square root 1 plus x squared. And that's our answer. So that's what this is equal to over here. And so that completes a few examples. Here are some other useful properties. Now most calculators have an arc sine, arc cosine, and arc tangent button built into them, but they don't have arc cosecant, arc secant, and arc tangent. Well, you can use these rules to evaluate arc cosecant, arc secant, and arc cotangent. So notice that the arc cosecant is the arc sine of 1 over x. And that's because cosecant is 1 over the sine. So it makes sense that this should hold. The arc secant of x is the arc cosine of 1 over x, and the arc cotangent of x is the arc tangent of 1 over x. So for example, if you wanted to evaluate the arc secant of 2, well, that would equal, using this rule number 2 up here, that would be the arc cosine of 1/2, 1 over 2. And if you use the unit circle diagram or your calculator, you would find that this is equal to pi over 3. And once again, if you just look back at the unit circle diagram, if I just scroll back there, so right here you see the cosine is the x-coordinate of all these points. Right here is 1/2 right here. So you see the cosine of pi over 3 is going to be 1/2. And so that's what we have right here. So the arc cosine of 1/2 is pi over 3. And so that completes this video on the review of the inverse trigonometric functions.